Okay, let's start the lecture. So this time, because for the last two lectures, we talked about water pollution. So how do we study the water quality, especially when you have some organic matter in the water? And then the second water pollution lesson was about the quality in a river, for example, in a water body. Okay, so this time we talk about how we human beings can do something to the water quality. Can we control the water quality? Can we make it better? So this lesson would be about that. So I don't know if you remember something happened in 2018 about the water quality in the public housing. So people found the lead in the drinking water, and the government officials insisted that there wasn't any problem, right? You can turn it on and then let it run for at least 3 minutes, which is not very practical, right? Every time when you want to turn on tap water, you don't want to wait for 3 minutes, right? So that's what they have suggested. So people found that the connection material in the pipes contain the lead. So the drinking water, actually the supply is not contaminated, but the construction within the buildings, they are contaminated. Okay, so this is one issue that we had a few years ago. And another issue, I don't know if you have heard of it, if you wash your cars on the street, it's illegal in Hong Kong. So the reason is that the two drainage system is not the same. So whenever you are pouring water on the street, it's mostly the storm water drain. So they go directly into the environment, which means that there's no treatment for this type of water. It's for storm water, it's for clean water, right? That's supposed to be clean. It's for clean water. But if you're taking a shower, for example, you wash your dishes, that drainage is going to the sewage system, is going to the wastewater treatment plant. So they are completely different. Okay. So I don't know if you have heard of the odor problem in the Chinwan coastal region. That's because the government has messed up one time. So they have connected the wastewater drainage to the stormwater. So the water goes directly into the ocean. That's why it's causing some odor problem. And they claim that it's already solved. Okay. I'm not sure, but that's what they claimed. Okay, so two different systems. So why do we care about drinking water quality? Of course, it's because we drink that, right? So if you have some lead, for example, so this public housing incident, so if you have some lead in the drinking water and you drink that for a long time, that would be harmful to different parts of the body, right? It's some heavy metal, right? Your kidneys, your blood circulation system, or even your brain. So it would hinder your intelligence development. So very toxic to the children, and also, of course, toxic to the adults. So we have to be careful when we do the construction, right? The lead could be in the solder material inside the construction of the building. Okay, so in Hong Kong, the Hong Kong government, we do have a water quality control system for the drinking water. So if we catch the water and we have a reservoir, the storage of the rainwater, actually we have the treatment factories here. So this is what you see. Sometimes when you are taking a bus through Tai Wai, the region, you would see something like this. So it's water treatment plants actually. And then after that, they would take some samples and they check the quality inside. So there's a government official doing that. And then that would go to your houses after that. Okay, so the water treatment plant is for drinking water. So it treats the water from the natural sources. And then the wastewater treatment plant, of course, is connected to sewage coming from your house and coming from different industries. Okay, and then after we have treated that, we check the quality, right? When we output the water and then it goes back to the environment. Hopefully the quality would be better. Okay, so two types of treatment plants in Hong Kong. So in this lesson, we'll talk about the drinking water treatment. Actually, it's not very much different comparing to the wastewater. Okay. So how do we define if the water is good or not before you drink it? Okay, before any of you drink the water, what do you see, right? You look at the color, right? When you open the tap and the water is brown, are you going to drink that? Of course not, right? You can see the particles inside the water, right? So we would expect, so this is the expectation, palatable, meaning that it's pleasant to drink, at least it's not brown, right? It doesn't have a taste inside, okay? And of course, it's so-called potable. It means that it's free of chemicals. So this is something that we might not see or smell, right? We'll have to do some measurement, okay, with the water sample. So to put that in a more objective way, so there are different parameters that we could describe the water quality. The physical, chemical, microbiological, or radiological. So 4 large categories. So for the physical parameters, so there are a lot of them. For example, the pH values. So we have talked about this, right? The amount of the H+ ions inside. We don't want your water to be acidic, right? Turbidity, meaning the clarity of the liquid. So if it looks like this, you're not going to drink that, right? High turbidity, the water. And why do you think that this is not drinkable? Okay, I will ask your intuition here. So why do you think that this water is not drinkable? You can't even tell what that is, right? But you know that it's something that you might not want, right? Maybe it's soil, maybe it's some organic material. You know that there are some impurities inside, right? So caused by suspended materials, and it may or may not cause you bad health effects, but you won't drink that, right? Anyway, so this is your suspicion, this one, okay? Turbidity is actually one quality, even if you can measure that objectively, okay? And then next is colorization. If it's looking like that, you're not going to drink that, right? So if it's red, the water is red, it means that there are some ions inside, and you don't know if it's drinkable or not, right? So the colorization usually are caused by different things. So organic materials from decaying vegetation or metals, metal ions, okay? So something might or might not be bad for your health, but of course you're not going to drink that. So sometimes it's not health related. Maybe it's taste, the odor, color. So one thing that the EPD has a very hard time to deal with is the odor problem, right? It's something that you cannot measure, right? Someone call EPD and then say, okay, there is a smelly source near my house, and what are you gonna do, right? It's just a smell. How do you measure that, right? Sometimes it's really hard to tell, right? So this one, unless you know that the source is toxic, right? I tried to call the government one time because I smelled something really suspicious. It's coming from some suspicious chemicals, I guess, and they found nothing. Okay, finally, all the firemen came to my house and came to my buildings, and they checked everything, and they cannot find the source. Okay, so next is conductivity. So if your water, if you put some current between 2 points and you find that there's a current, the current is connected, then you know that some of the materials inside can allow a current to go through. It means that there are some impurities inside. So conductivity is one of the things that we really can measure. And also, of course, temperature. If it's too high, then you know that there might be some source doing thermal pollution to your water source here. Second one is chemical properties. It might be more objective here because it's something you can measure. For example, the heavy metals. So for the Hong Kong officials, Hong Kong governments, they measure 12 of them. Maybe the most prominent ones would be lead and mercury. Okay, and also pesticides coming from the farmland. Also disinfectants or disinfection byproducts So chlorine, right, is something you smell in the swimming pool, okay, or other inorganic chemicals like fluoride. Actually, in our drinking water, we have that. So the government add the fluoride into our drinking water on purpose. It's for dental health, okay? And also organic chemicals, some carcinogenic material like benzene here. So this is how they do the measurement. They have a unmanned small ship or small boat in here, and they go to take the sample in the water body and then take that back to the lab. Okay. Okay, the third category is microbiological properties. So there are a lot of different types of disease-producing organisms, meaning pathogens, okay, including viruses, bacteria, so different small or microorganisms or worms. And the main source would be, of course, coming from the discharges from animals, right, or from us, okay? And what do we check? We have so many different types. We usually just check one type, which is E. coli, okay? Because the belief is that if this type of bacteria is a lot in the amount, other types of disease-producing organisms would be having a large amount. Okay, so this is like an indicator for the whole water quality system. And why do we measure this one? Because it's very, very common to see in the nature, large quantity, easier to measure in the lab. So you can even see the growth in the lab comparing to other microorganisms. And the analysis is very cheap. Okay, of course, we want to go for the easy way, right? When we when we do measurements. Okay, the fourth one, the government also checked this, is the radioactive materials present in the environment. Okay, so the processes, why do we have radioactive materials? Due to nuclear testing, for example, mining or the operation of the nuclear power plants nearby. So this is a very hot topic these days. So different governments are trying to measure the radioactive materials in the ocean water, right? Because of what Japan is doing. Okay, so in Hong Kong, we only measure one thing, which is the alpha decay, the alpha particle coming out from this type of radioactive reaction. Okay, instead of individual radioactive materials. Okay, so I am showing you this because this is very hot topic right now. So Japan is dumping a lot of radioactive water into the ocean, and we are yet to see the effect, right, around the whole world, not just for the seafood, right? Okay, and it's going around the world through the ocean circulation. So I don't think it's enough to just ban the seafood from one country, right? We should ban the seafood from all over the world because of this. Okay, so before we talk about treatment, we need to talk about what type of properties we are dealing with, right? So if you talk about different sources of drinking water, for example, groundwater here from the aquifer, or the surface water here, they have different properties. So we need different types of treatment plants before they come into our houses. Okay, so groundwater, maybe they are from wells. Surface water from rivers, lakes, or reservoirs. So two types of sources in here. So how does the, why do we need to treat the water? Because it's contaminated, right? There's some contamination, or there's some properties that we don't like. For example, if we have some colors, even if it's white, right? In your drinking water, you don't like it, right? So this is one way to have contamination in groundwater. So you think that you are living far away from the landfill, but sometimes it's not far away enough. Actually, you are drinking the water, the groundwater, which is the same groundwater underneath this landfill. So of course, there are a lot of toxic materials, right, coming from the landfill, and there's leakage into the groundwater, and you end up drinking that, or contamination to even the surface water here. So you think that, okay, the groundwater is contaminated. I'm taking water from the river and it's still contaminated because of this. Okay, so other types of contamination, for example, if you have some livestock in here, you might have some manure, so the excretion from the animals here into this water body, into this river. So you might want to check the E. coli amount, right? The bacteria amount in the fresh water source. Okay. Also, there's leakage into the aquifer. Okay, why do we care about this? So this is actually imported into Hong Kong a while ago. So this kind of lettuce, romaine lettuce here. So I myself don't eat salad a lot. That's why, because it's uncooked. When it's uncooked, then there might be some microorganisms, sorry. So different properties here comparing the groundwater and the surface water, right? For the groundwater, maybe they have constant compositions because mostly it's coming from the rainwater, right? The rain coming from the sky and then fall onto the ground, right? So that's the source for groundwater. And for the surface water, because it's coming from underground, right? It might be going through different layers of rocks. So it might contain different, oh, sorry. I've messed this up. So groundwater has constant, I don't think it's constant compositions actually. If you are looking at different locations on Earth, the minerals might be different. So high mineral contents. And for the surface water, variable compositions, probably different types of soil. So they have different compositions or they are contaminated by different sources. Okay, even if it's rainwater. Okay, and low mineral contents because it's not going through different layers of soil. Okay, and underground, if you have so many mineral contents here, the hardness is going to be high. So hardness is a measurement for the amount of these kind of ions. So when you go traveling in the US or in Europe, this is what you see when you boil the water. So this is coming from the ions. In Hong Kong, you're not going to see this, right? Because the government has dealt with the ions inside the drinking water. Okay. And for why do we talk about this? Because when you want to treat the water, you need to know what type of properties you're dealing with. For example, in the groundwater, the job is to remove the hardness, right? This is scary for some people, right? So you want to remove the hardness. For the surface water, maybe the main job is to remove the turbidity, right? Maybe there are some dead leaves or dead tree bodies inside the surface water. You don't know, right? Or a lot of dead animals remains. You don't know, right? You need to deal with that. So different properties here. Microorganisms, of course, they're active because they have access to different nutrients, right? So you need to remove that before it's coming to our houses. Okay. Maybe groundwater bacteriologically safe because the bacteria, there are fewer types of bacteria that would be active underground. Okay. Possible chemical toxicity coming from the contamination, of course, it's the same for the surface water. And some people believe that underground water is safer because you have different layers of soil to do the filtering, right? Actually, our water filtering system, some part of it is mimicking what they have in the nature. Natural filtering capacity, okay, remove suspended solids and turbidity. When water is going through different layers of rocks, some of the smaller particles would be retained, right? So it's supposed to be cleaner. But if it's contaminated, it takes a very long time to clean for the groundwater because it's in the ground, right? And it's moving very slowly, okay? Okay, so two types here. For the Surface water, it tends to have higher turbidity. That's why we need to remove. So the main job here is to remove the turbidity here. And for the groundwater, the main job is to soften the water, remove the hardness, so-called hardness, meaning the metal ions inside. That's what we expect, right? We expect the water to be transparent without any impurities. Okay, so how do we treat the surface water? So this is how we treat it. For the surface water, we need the so-called coagulation plants here to remove the particles. So next part we'll be talking about that. Okay, so what's coagulation? So it's very, very simple idea. We put some coagulant, the so-called coagulant. It's supposed to be sticking the impurities together here. So it's not like air pollution, right? Air pollution, we wait and wait for the pollutants to go away. But here in the water, they won't go away, right? So we want them to stick together, and then we remove that. So on the left-hand side, this one is hard, very hard to remove the impurities. But on the right-hand side, because they stick together, we can just scrape it off, okay, from the bottom of this treatment process. It's called coagulation. Okay, so there are two types. The first one is called coagulation. We just talked about that. So it's a chemical process. You put in some positive ions here, or adding some. So if of course beforehand you know that the impurities are having negative charge, and you're adding positive charge so that they can stick together. Okay, and then you have some larger particles, and you remove them. And for the other one, it's called flocculation. It's very, very similar to this coagulation. It's a physical process. We still put in some positive charge, but there are some fiber-like material here. If you put that inside, you will shorten the distance between the negative charge, and then they stick together. Okay, either way, so for the first tank in here is coagulation, and for the second tank in here is flocculation. And after that, we expect the impurities to stick together and sink to the bottom. And this is called wastewater sludge, woolite. Okay, here, this one. So we are trying to scrap this off, and then this water is treated. Okay. So there are different types of coagulants for the positive charge in here. So there are chemicals added to the water to make the impurities sticking together. And there are different types. Of course, the name here is just telling you how many positive charges from the ions. So molecular 1 positive charge, divalent 2, and trivalent 3. Okay. The chemicals here should be non-toxic because we are drinking the water, right? So the trivalent here, the third kind, is more effective. So this one is the example is, I think, what's the name of that? It's called alum, I think. Okay. So we are putting this inside. This will be ionized in the water, and we will have the free positive charge in the wastewater or drinking water. And then we hope that they would stick together after that. Okay. And the free positive, so these two are talking about the trivalent here, the example for these two. Both of them will give you free positive charge for the positive ions. Okay, so if you go back to the engineering graph in here, it's not going to look like this if you look at the floor plan of some water treatment plant. Okay, so first of all, you would see the source here on the left-hand side, and then the first part is screening. So you probably need to screen whatever obstacles or objects in your water, right? Maybe some people throw in some garbage in the water, and then you have to do the first type of screening. right? The larger objects are screened. And then after that is the first sedimentation, primary sedimentation, further remove the large objects inside. And then after that, you might want to add the coagulants inside. So this one is referring to the orange one here. So these two are equivalent. And then flocculation is the second one. So you have some fans inside to increase the mixing. And then the third one, this one is secondary sedimentation. So this one is supposed to be collecting whatever you have. So you have some sticking together action, right? The coagulation and flocculation tank. And then they will stick together and then you wait for the sedimentation. And for the both sedimentation process, you will collect the sludge. The sludge is solid. So what we do with it is that we have some transportation system. We have some cargoes or vehicles to transport that away to the location where we can burn that, because it's sometimes or most of the times it's organic. We can burn that for energy. Okay. So it's a talk for another day. Okay. Not today. So next, we'll get to the next part. So this is just talking about the middle part. So how do we know how much coagulant we want to add? So here is coming from the measurements. Okay, if we want to add, for example, aluminum ions here, or calcium ions, or potassium, I guess. Okay, different types of positive ions here. The x-axis is telling you the dosage. So which one do you want, judging from this graph? X-axis is the dosage. Of course, you want the lower dosage, right? You don't want to buy too much of this material, reduce the cost, right? So that's why this one might be more effective. For the lower dosage, you can reduce the turbidity to a certain level. So you want to reach here, right? Just this dosage would be enough, okay, to remove or to reduce the turbidity to 0. Okay. And maybe for these two, you will need a higher dosage because you're on the higher side of the x-axis, right? And this is another example showing you another type of coagulant. And sometimes they give you a U-shaped curve. It means that if you're higher, let's say if you're here, you're already having 0 turbidity. And if you increase the dosage, the turbidity would come back. So this is what we call overdose of positive charge, and you don't want that. Why do we have this overdose situation? It's because you're adding too much positive charge, and the positive charge starts to repulse each other again. So you're going back to higher turbidity. And you don't want that. So whenever you want to add the coagulant to your water, you might need to read this graph first. Okay, so this is the chemical. This is showing you the example for the aluminum ions. So it's called alum here. So this type of, this one, I think this is the first example here. Aluminum sulfate. Okay, this one, yes, I have it here. Okay, so when you add this into the water, your material would be ionized. So there will be some positive charge here, and the positive charge is supposed to be sticking your impurities together. So this is what you see when you add the alum inside. So what do we expect? We expect that, so the second, for the first one, we have the graph like this, and for the second one, where we add that alum into the water, we are trying to remove the alkaline situation, right? Alkalinity. So when we are doing this, we will get the insoluble material, which is looking like this. Okay, and we can remove that if it's solid. Okay, so next we talk about the rationale behind the flocculation is very much the same idea comparing to what we have for the coagulants. Okay, so here I have a graph showing you the different forces happening for the impurities. So if you have some impurities with negative charge here, and if it's very far away, so the x-axis in this graph is telling you the particle separation. So if you're really far away, the two charge here really far away, and you're sitting here, the repulsion, the red curve is higher than the attraction. So they are supposed to repulse each other, right? The attraction is very, very small, even though you have, of course, everything attracts each other, but it's very small. Okay, so how do you overcome this so-called energy barrier? So here we are trying to add some positive ions or coagulation, which is what we have done on this graph, so coagulation. And for the second method, which is adding the fibers or so-called the polymers, if you're adding the polymers with negative charge, you are reducing the distance between them, right? So you are overcoming this energy barrier. And if you're reducing, so the effective distance, I would say, if you're reducing the distance between them and they are closer together, the attraction is supposed to be larger than the repulsion and they can stick together. Okay, so the long chain carbon compounds that have many active sites, so in some way they are connected, right? The fibers or the polymers are doing that. Okay, so how long do you have to wait? Okay, now you have added the polymers, you have added the coagulant. How long do you have to wait for the water to sit inside the tank? So there is some calculation that we can do. So let's say if you have some impurities in here and they are already sticking together, okay? And you have to wait for them because they're solid, right? They are going to fall to the bottom of this tank, but you have to wait because you know that water also has some very large friction or viscosity inside, right? You have to wait a while. It doesn't just fall like within an instant, okay? So maybe for a few hours, your impurities would sink to the bottom and you have some clear water and you can scrape this off, right? On the bottom of this tank and you're done, right? So it's done by mechanical scraper. You need to use electricity to remove that, okay? So this kind of tank, we call them settling tanks or clarifier. And so how long do we have to wait? So now we have to deal with the calculation now here. So the area here is actually talking about the bottom, actually, the bottom area, but we will get to that. Okay, so the average velocity. So if you are owning this wastewater treatment, just like what we have done for the assignment, what's the volume flow rate, right? If you're owner of this treatment plant, it's a very important question. So how much water you are dealing with every second, right? That's an important question. So the water volume control rate is Q here in this equation. And A is the cross-section surface area. What's V, actually? V is the water velocity if you do the division here. This is the unit for this. So water going in, water going out is this water velocity, okay? Actually, the cross-sectional surface area should not be this one. It should be the bottom surface area because when you increase the water volume, you're increasing, we have gravity, right? So you're increasing in this way, right? Or and you're decreasing in this way, right? Okay, so there are different forces acting on the impurities here. Let's say if we have a laminar flow, if we have a turbulent flow, it's a topic for another course. Okay, so if we have laminar flow and we have different forces acting on each of them. And we want to calculate the velocity of the impurities. How do we approach this? We have to study the force diagram here. Okay, so of course you're sitting on Earth, right? We have gravitational force. And then the second one is buoyancy force, because there should be some pressure coming from the water. That's called buoyancy force. So this is buoyancy, and in case you don't know, okay, a part of your ship is submerged in the water, and that's replacement is going to give you a buoyancy. Okay, so whenever you see a very, very big ship, actually the submerged part is very large because the ship is very, very big. Like you just don't see it. Okay, so that's the buoyancy part, this one. So buoyancy, and then the drag force is coming from the friction, the so-called friction, resistant force caused by an object. So if you're running like this, the drag force would be going behind you, right? The air is supposed to slow you down. Okay, so you are moving downward, so the drag force is moving upward. Okay, so 3 forces in here, right? And in this course, we will not talk about calculus. Okay, so we will just get to the balance part. So the drag force, so the equations on this slide is optional, but I'm trying to explain how we get to the equation that we're using. Okay, so the drag force is coming from the drag coefficient. Yeah, this one. It's also for another course if you want to know about this. Okay, so the drag coefficient is coming from the properties, the shape of your impurities. And we assume the shape of this impurity is a sphere here. So the diameter contributes in here. Okay. And also the density of your impurity goes into the equation here. So it contributes in the drag coefficient. Okay. Anyway, so the properties of your impurity goes into the drag force, and you have the expression for that. And of course, we have the expression for gravity, just mg, just Newton's law. Okay. And we have the equation for the volume, right? Assuming that this is a sphere. And also we have the similar expression for the buoyancy force coming from the shape of your impurity. So 3 forces in here. Okay, so let's say if you release the impurity inside the water, what happened? At first, there would be only gravity and buoyancy. Okay, gravity and buoyancy. Buoyancy is always there, and gravity is always there. And if you release your impurity from rest, because you have no velocity, you're not moving. If you're not moving, there's no drag. Okay, you don't have drag yet. Okay, and then after a while, because you're moving faster and faster, right? So you have some drag force. The gravity is still larger than your drag force plus your buoyancy force. The forces are not balanced in this situation, and your speed will increase and increase until you reach a so-called terminal velocity, the highest a particle can get. Okay, the highest velocity a particle can get. So the 3 forces, they balance each other, and then your impurity does not move with an acceleration, right? It's a constant speed. Okay, so no calculus in here. Okay, so we assume that the 3 forces equals to each other. The steps are optional, so this is given to you in the exam. Okay, you will have the terminal velocity for impurities. How do we calculate this? G is just gravity, and rho p is the density of the particle. You have to take some samples to the lab and calculate or find out the density of your impurities, maybe the average one. Okay, you're having an estimation. Okay, rho is just density of water. You already know that. And D is supposed to be the average size of the particle, diameter of the particle, this one. Nu is the viscosity of water. So viscosity is very important in calculating your terminal velocity, and that's it. Okay. So why do we care about the terminal velocity? Because we don't want the water to go through this tank so fast, and the particles are not settling on the bottom, right? If it's so fast, then it doesn't settle onto the bottom of this tank, then you cannot remove it. Okay. So what do? We study the dimension of your tank. So let's say if you have water coming in from the left-hand side, water going out from the right-hand side, okay? And your particle, of course, is going to the right, right? The water is coming in from the left. So there is a rightward movement, but that's not what you care about. You care about the downward movement, right? Whether it's reaching the ground before it's leaving the tank, right? You want that. So you have some settling particles path in here. So it's going down and going to the right, right? And you do have, so this is how you calculate this vertical speed only, right? We only care about the vertical dimension here, okay? So the velocity should be equal to this HP, so the height, the vertical distance of this, the traveling path of this particle divided by T is the vertical speed, right? So T here is the detention time. So how much time your particles is going to stay inside this tank, right? We have the expression for this because we already have already have the equation in here, this one. Okay, maybe I'll get to this later. Okay, let's look at the left-hand side in here. So for the particle to settle at the bottom, we want this HP, the height for the particle, to be larger than the height of the tank, which is the H here. Right? We want that to be larger, and we divide the both sides by T, which is the detention time. And we know that your particle velocity should be larger than some velocity, which is V0, which is what we call the critical settling velocity. So your velocity should be higher than or equal to V0. So you can calculate V0, right, from the size of your tank, right? And how do we relate that to what we have learned? So V0 here is like a standard speed. How do we relate that to what we have learned to the volume flow rate? So this is how here. So the settling velocity equals to the height of your tank divided by the detention time, right? And after that, we can use the equation and turn that into volume flow rate divided by the volume of the basin, right? Volume flow rate is cubic meter per time, and then this is just cubic meter, right? So turn the time into the two volumes in here. The first one is volume flow rate, second one is just volume. If you do the division, you will get the time back, okay? And volume of the basin, you can turn that back to the basin area here times the height, which is the total volume. You can divide, you can cross out the H, right? Finally, you have the volume flow rate divided by the base area, okay? Not the cross-section area, actually, the base area, because water is going up in this manner, right? We have gravity. Well, it is always in the horizontal plane, right? In your settling tank, okay? So that's why we get the equation in here. So this is how we get the equation. So this is wrong, okay? So the area showing here is wrong. It should be the bottom basin area. So this water velocity describes how fast the water moves in the tank. Actually, it controls this one. Okay, so it looks like that they're not related. This one is just going in, and the velocity of your particle should be coming from this one, right? So it looks like that is not, but it's controlling how fast. It's not controlling how fast, it's limiting the time that your particles is staying inside the tank. And V0 is also known as overflow rate. So the unit is still this one, the speed, or you can use the unit here, the volume flow rate divided by the area. So the volume flow rate is cubic meter per day by the area. Okay. So it describes the settling velocity, which is this one, right? It's coming from what we have proved in a few slides ago. Okay. This settling velocity describes how fast the particles settle. So I'm sorry about this. So your settling velocity should be larger than or equal to the overflow rate. This is the requirement when you want to design your settling tank. Okay, so this is an example. It's asking you the terminal velocities of some particles here with the particle density given to you, and you just use the equation in here, right? So G is just gravity, and this one is particle density, which is this one, right? Particle density, and rho is the density of the material you're sitting inside. So for air, it's 1.17 here, this one. And for water, it's 1,000. So this is the only difference between these two, okay? And of course, the viscosity is not the same. Which one has a higher viscosity? So it's asking you which material is more sticky. Of course, water is more sticky, right? This one. When you want to pour some water, when you are done with a cup of water and you want to pour that to the sink, you have to wait a while. That's the viscosity. Okay, it's higher for the water, and you can see that the terminal velocity, if you use a settling tank with air inside, here, this one, it might be faster, right? This one is higher. This one is slower in the water, but this lesson is about water quality control, so it's very, very slow. Yeah, this one. Okay, maybe we can take a break for 5 minutes first. Okay. Okay, let's continue. So how do we scrape off the sludge? So it's mechanically scraping off. So there are some pulley systems. So some wheels here, and then there is a circulating belts, you would say that. Okay, and they are supposed to scrape off the sludge sitting on the bottom of the tank. Okay, there's sludge collection. So the sludge is moved to one side, and then we can collect the sludge. Or it's in a circular motion. The sludge scraper arm here is supposed to going around. So this, if you look at it on the top, it would be a circular shape tank. And then you will collect the sludge from below. Okay. Okay, so this is an example for a clarifier or a settling tank. So the treatment plants here is supposed to receive this much of water per day. So this is very important, right? How much water you're treating every single day. Okay, and this clarifier, you know that it's a circular shape. Usually it's circular. Okay, and it's to be designed to have average detention time. So the water is staying in a tank for at least 2.5 hours, and the average overflow rate. So it's giving you the V0 overflow rate. It's 20 cubic meter per day per square meter. Okay, so overflow rate is given to you. What should be the dimension? So this is very important, right? Before you have, you build the water treatment plant, you have to know how much water is treating every day, just like what you have done in the homework, in the assignment 1. Okay. So you know that this overflow rate is 20, right? 20 cubic meter per day per square meter. And Q is the volume flow rates that you need. Okay, then now you already know this one, right? This the basin area of your clarifier. What would be that? Just 15,000 divided by 20, which is 750 meter square. Okay, and you can turn that back to diameter of your clarifier here. And what's the question is asking you? What should be the dimension? So you have found the diameter. What about this? Oh, you have also found the area. Okay. So I think we are, okay, A and D. And what about the depth? We can make use of the detention time from the equation here. Okay. B is the volume, and we know the detention time is given to you, right? 2.5 hours, 2.5 hours here, and volume flow rate is given to you. So which means that your detention time and the volume flow rate is constraining the depth of your design, right? The depth is here, surface area times the depth is the volume, right? And you know that the depth is 2.1 meter high. Okay, so this is what you see when you are taking a bus and go through Sha Tin or Tai Wai, some area in Sha Tin. Okay. And where does the sludge go in Hong Kong? We have a facility called T Park. I think it's in Tuen Mun. Okay, the sludge is transferred to this T Park by some heavy vehicles. They will transfer that to which means that we might, before we burn that for energy, we have to use some energy to do the transportation. Okay, the sludge is the water. Of course, if you want to burn that, you need to remove the water and burn that to provide energy. So the spa here is supposed to be using the energy coming from the incineration of the sludge. Okay, it's free. You can have some reservation there. Okay. So this is what we do. We use some vehicles to transport the sludge to the facility here and for the incineration, right, to get the energy. So it's the same as burning any type of fossil fuel. Okay, so we have done talking about the coagulation or flocculation or sedimentation part. What about the next part? For the next part, so it's supposed, so for the first part here, it's supposed to be removing a lot of impurities from the coagulation. And after that, we are trying to remove smaller particles. We'll do that by filtration. So what's filtration here? It's a very, very simple idea. So we put the water here, and the water goes through all the layers of solids in here. So they are going in between the very, very small spaces between the soil and the rocks in here. And then after that, we can collect the treated water. So this kind of filtering system, sometimes when you buy a water filtering system for your home, okay, you install that to your tap. That's also the same idea behind that. And this kind of system, it needs frequent washing. Actually, we need to wash that every now and then. Just reverse the water flow. So you supply some clean water and then clean this filtration system. Okay, so the next part in this graph is this one, disinfection content. So this part is supposed to be dealing with the biology, right? The microorganism inside. So we need to kill the pathogen organisms, bacteria, viruses. So sometimes we supply chlorine. That's something that you can smell in a swimming pool. We sometimes add the chlorine as a gas to the water that we want to treat. So water here, for this equation, water here, and then you add chlorine gas, and then you will get some exit inside. So this is the major or the prime disinfecting agent. So it's supposed to be killing the microorganism. But so this is what we call the free available chlorine, this one, free available chlorine. But oh, not the dash line, this one, sorry, HOCl, this one. So you can see that in this graph is showing you the percentage of free available chlorine. So FAC here is free available chlorine. Okay, so you can see that if you want to keep the free available chlorine to be high concentration, you need a certain pH value, right? So it's pH dependent. Okay, sometimes it's why do we lose a part of it? Because it can be further ionized into the two components here, which is less effective. Also free available chlorine, but it's less effective. So we want to keep this as high as possible in the water. Okay, so there are some pros and cons for using chlorine as the disinfectant, right? It's very effective against bacteria, not expensive, reliable. So by reliable, we are talking about the effectiveness, right? It's always effective. And it provides some residue in the distribution system, which means that some of it is left behind. And it destroys the unpleasant odor causing compound. So it destroys the unpleasant smell. But of course, it could form toxic components when it's combining with some organic substances. So it could be toxic and less effective against some type of microorganisms like protozoa here, this one. I have no idea what that is, so I'm showing you a graph here. Also virus, okay, maybe more effective towards this type of microorganism, okay? So this is like a summary of what we have talked about. First of all, we do the removal of large solid waste screening. By screening, is really screening, okay? You have some, it's like your air conditioning where you have some sort of windows in or sort of grids in front of your air conditioning, and it's supposed to be blocking the large particles, right? So after that, primary sedimentation, the first sedimentation, and then we have coagulation, flocculation, so sticking the impurities together, 3 and 4 here. And then the second sedimentation is dealing with impurities coming from these two, and then filtration, disinfection, okay. So we have talked about the coagulation plants. So next part is the softening plants. How do we remove the hardness? So it's, of course, it's supposed to be for groundwater treatment because groundwater has higher hardness. So where does the hardness coming from? So let's say if you have some precipitation and then your precipitation, the water goes through all the layers and it collects something on its path. And what does it collect? It collects some acidic, it picks up some acidity here. This one is acidic, right? So when you have some excess, so the excess is coming from the carbon dioxide in here. So water combines with carbon dioxide and we'll get the excess in here. So the excess is kind of removing or dissolving the material in limestone. Let's say you have a layer of limestone here and removing that, and the calcium and magnesium ions are actually what we are calling water hardness here. So the presence of calcium and magnesium ions. Also, there are some other types of ions. So they're all coming from the rocks, okay? Because you have some acid in the rocks. Okay, so where do we see this kind of hardness? So if you go traveling in the Western countries, sometimes this is what you see, okay, in the bathroom, because the ions there are accumulation of the ions on the wall that's coming from the water. So even if you're cleaning that very frequently, you will still see something like this. And you can also see that inside the pipes, the deposits inside the pipes. Okay, so how do we quantify the hardness? We use the equivalent weight. So very simple idea is the weight per unit of charge. Okay, so for the calcium, the weight of one calcium, the molecular weight of one calcium, you can check that from the table, is 40 grams. So we have talked about this in the environmental chemistry lecture. So 40 grams, and you know that it's 2 positive, right? 2 charge. So per charge, you will get 20 milligram in here. It should be milligram. Should be gram or milligram. Milligram. It should be milligram because this is milli charge. Sorry, we have added an M on both of the units. Okay. Okay. So 40 grams of calcium ion, 2 positive charge, which means 20 grams of calcium ion, 1 positive charge. Okay. And we use this milli charge unit usually. Okay. Because we don't have 20 grams of calcium in water. We have 20 milligrams most of the times. So this is the unit we use. Okay. So for the calcium carbonate, we do the same. So we add calcium, the molecular weight is 40, carbon 12, and O is 16. So 3 O here times 3. So the altogether, we have 100 grams of calcium carbonate per 2 positive charge, which means 50 grams. So after that, you will find 50 milligram per milli charge. Okay. So how do we make use of the concentration that we have? So here, 1 liter of hot water, what we want to ask is the concentration of the calcium carbonate. So if this is what we call the hardness, how much of that we have? So concentration is what we had already learned, right? But here in this lesson, we are going to ask about the charge, right? 1 liter of hot water, how much charge do we have, instead of asking the weight, right? So how do we calculate that? Making use of the concentration. So here is how much charge we have per liter, right? How much charge, milli charge, or okay, we have per liter of some material. So we just use the concentration, something that we can measure, and also something that we can calculate. The green one is what we can calculate, right? Directly from the table. You don't need to do measurement. What you need to do is do measurement for the concentration. Okay. So if you do division here, you will find that it's the same unit as the milli charge per liter, right? If you do look at the unit here, the top of this fraction is just concentration, milligram per liter. The bottom one is milligram per milli charge. Okay, and we can cross out the weight. Okay, it doesn't matter here. The weight doesn't matter. So now you can just do measurement for the concentration of calcium divided by 20. That will be your hardness. Okay. So this is pretty simple. So how do we calculate the hardness? Just use concentration that you can measure divided by what you can check from the table. Okay. So the next part is how we standardize different types of ions. So this is an example for calcium ions. What about magnesium, right? What about iron ions, okay, or aluminum ions? So there are different types of ions in here. We need to standardize or normalize the numbers so that we can do comparison. So how do we normalize different types of ions. We multiply the whole thing by the equivalent weight of the calcium carbonate. Okay, this is like an industry standard. Okay, don't ask me why we use calcium carbonate. So this is like a industry standard. If you check the standard table, that's what you see. Okay, we'll get to that. So multiply both sides by the equivalent weight of calcium carbonate, the orange one here, and the concentration of calcium carbonate can be used to estimate the hardness. Okay, so we turn everything to the numbers for calcium carbonate. Okay, so what you had just calculated here, you can just multiply the whole thing by 50 milligram per milligram of calcium carbonate here. So what you have here, multiply 50, and then you have the concentration of something. It doesn't have to be calcium, right? It doesn't make sense, right? You're using calcium carbonate to represent calcium, right? Let's say if it's magnesium or ions. Okay, other types of ions, you use the concentration unit here again to represent the hardness instead of using this millicharge per liter in here. Okay, so you can check the equivalent weight from the, actually you can calculate that on your own, but you can check that from the table. The table will be given to you if you're asked to do this kind of question. So aluminum, you have 3 positive charge here, so 27 divided by 3, which is 9 equivalent weight. And another example, magnesium here, 24.3 molecular weight divided by 2, so 12.2 milligram weight per milli charge or milli charge. Yeah. Okay, so this is an example to calculate the total hardness. So it's a little bit more complicated because this water contains calcium ions and also magnesium ions. So we just add them together actually. So we calculate the charge per liter for calcium first. So 100 is given to you by the question. 20 is, you can check that from the table, right? That's calcium here, this one, 20 milligram per millicharge, which is 5. And then you do the same for the magnesium, 12.2. You can check that from the table here, this one, 12.2. Okay, so we add them together because now you have the same unit, right? Millicharge per liter, add them together, which is the total hardness 5.8 millicharge per liter. Okay, and the second part is asking you, so they are, both of the sub-questions are asking you the total hardness, but the first one is represented by this unit, and the second sub-question is asking you this unit, which is a concentration unit as calcium carbonate. So if we turn everything to calcium carbonate, what would be the concentration? That's what the question is asking you. If all the hardness is coming from calcium carbonate, what would be the concentration? Okay, so very simple, just multiply the whole equation by the equivalent weight of the calcium carbonate, which is 50, right? So you do the same for calcium, just so 120 is what you had for part A, right? Just multiply by 50, just this one, and then do the same for the magnesium and add them together. Actually, you can just multiply this 5.8 by 50, then you can get the answer, which is 291. You don't have to multiply it separately. Okay. So why do we have 2 numbers for the same hardness? Okay, we are trying to quantify the hardness. So this one is represented by 5.8 millicharge per liter. This one is 291 milligram per liter as calcium carbonate, because sometimes people use the standard for millicharge per liter. Sometimes people use milligram per liter as calcium carbonate. So you can check the table to see if your sample is hard or not. Okay, so 5.8, this one, Where is it? Okay, it should be hard. Okay, not very hard, but hard. Okay, and this one is 291, which is also this one. Okay, so it's categorized as hard. Okay, so how do we deal with this kind of water? We have to do what's called softening. Okay, so there are different methods. This is showing you one of the methods. So let's say if you have some hardness, which is coming from the blue elements in here, calcium, magnesium here, we add the so-called the lime inside, which is this red, highlighted in red in here. Why do we add this lime slurry? Because we are hoping that this would become the calcium carbonate, which would become the sludge. So calcium carbonate in here, sedimentation of solid forms, they would become solid. So there's a bracket here showing you that it's a solid, and we can scrape that off from the bottom of your or sedimentation tank. Okay, so wastewater treatment. So this is the last slide. I just want to add one more thing to this lecture is this one. So bioreactor. So for the wastewater, we have to add some more to your system, which is dealing with the organic matter inside, right? We have talked about this. How do we deal with the organic matter, which is this one, but it will not be covered, okay, in this course. Okay. So if you have questions, you can come down and ask me, okay? And then next time we'll do the tutorial, okay? Thank you.